Hello everybody, my name is Mark Sage and welcome to the latest Area Research Committee webinar. And we'll be talking about 3D capture and AR for subsurface utility engineering. It's a really interesting, exciting area, and I'm really pleased to have you here today. Leslie, can you move to the next slide, please?
Sure.
Just real quick, and some of you will already know this, but an introduction to the area stands for Augmented Reality Enterprise Alliance. And as you can see, we're a global membership-funded not-for-profit alliance, really helping to accelerate the adoption of enterprise AR. And these thought leadership webinars and ability to kind of share this information is one of the important value propositions that the area wants to give to the ecosystem. Next slide, please, Leslie. To give you an idea, our members are in 3 different segments. There are the companies that are deploying the technology. And whilst we'll be focusing a little bit more on utilities today, we actually see that all sorts of industries can make use and are benefiting from the deployment of AR. So it's all about the use cases and the problems that are being solved. We have a bigger group of the providers of technology, including the hardware and the software companies. And I'm sure some of you have been either working for or been working with these companies. And we also have a third segment, which we call non-commercial organizations, who are non-commercial organizations. And it's a combination of government agencies, research institutes, universities, and standards organizations. So the kind of ability to come together as an ecosystem, to learn from each other, and to develop kind of best practice in thought leadership is really important. Next slide, please. Just to give you an idea of what we do, we focus on what we call our 4 strategic pillars. The first one is a great example of what we're doing today. It's about delivering that thought leadership, the kind of information that business decision makers need and want to understand to help them deploy the technology. The second one is networking. We find it's really important to bring the different players together, really to learn from each other, to share those experiences and build those partnerships. You know, we unfortunately see far too many projects that get stuck in pilot purgatory, but by learning from and working with other companies, we're able to help the ecosystem come out of that pilot purgatory and deploy it wider within the organization. The third pillar is around educate, and what we find at the moment is there's definitely a skills gap. That's partly to do with how fast the industry is moving. And what we are doing is working with universities and educational organizations to help them define courses, offer guest lectures from our members, outplacements, and anything we can do to bring that next set of skilled workers to the industry. And then finally, and probably where most of the work's going on at the moment, is about reducing barriers to adoption. I mentioned the term pilot purgatory. Lots of companies are trying the technology, but often there's barriers to adoption, which are quite often business barriers as well. So we have a number of committees that meet on a monthly basis to look at some of these barriers, including security and safety and developing a set of requirements and human factors. And an important one is the research committee, which today is an example of some of the outreach we're doing, the thought leadership from the research committee. Okay, Leslie, just on to the next slide, please. To give you an idea, this is not the first webinar we've done. In fact, we've done over 40 in the last 4 or 5 years. So it's a huge and really important resource. So please feel free to go to the area portal and look under the area resources for the videos. And there's lots of information there, and also our area YouTube channel as well. So please try and make use of those resources. Any feedback will be great, and feedback to myself or through the area website. Okay, last slide, I think, from me. Oh, no, sorry, just to say there's lots of other events. If you go to the events page, you know, the area is collating events and also running lots of different events as well. So it's a great opportunity to meet the area members and get involved and engaged. Okay, next slide. And I think that really is. Yeah, so I'm just going to pause here. I'm going to be handing over to Lassie, who's been taking us through his kind of presentation. But there are opportunities to make any questions that you have within the GoToWebinar control panel. There's a questions box. Please feel free to type in anything there. We will be taking questions at the end. but do it anyway, part through the meeting. We do like to engage at the end with any questions. If we can't answer them all, we'll certainly follow up afterwards. And this webinar would be made available to everybody through the area website, and we'll send you a link to that when it's been completed and up on the area website and YouTube channel. Perfect. I'm going to sit back and looking forward to listen to Leslie's work. Leslie, if I can hand over to you and you could take us forward. Thank you very much, sir.
Thank you. Yeah, thank you for the introduction, Mark. First thing I would say that I was supposed to also have my colleague join. He is unfortunately a bit late, but he will maybe come in later and do the second part of the presentation, or he wasn't. In fact, he should have done the first part. So I'll just start with my part second, which is really, more about augmented reality and how we visualize subsurface utility data. And just short about me, I'm doing my industrial postdoc right now at IT34, and together with Aalborg University from Denmark. I just finished my PhD, and it's also primarily the work I did in my PhD I'll be telling you about today. So let's get to it. So part of the title Subsurface Utility Engineering, this is surrounding topic of what we were talking about today, because if you look at that, that's actually a profession and a task that engineers and has to do in the field. And what is it really? It is the way to how we nowadays locates subsurface utilities. So in traditional ways, it's either by looking at utility maps and then you apply that on the streets with utility markings, or you take more advanced equipment like ground penetrating radar scans, or simply if you can't find the utilities, you simply have to do what's called daylighting, so slow and careful digging until the utility assets are exposed to daylight. And really within these information workflow of subsurface utilities, what I realized was that we need to have better ways to either capture and manage utility data, and this was really the part Rasmus was going to talk about, which we'll talk about later, and then also communicate and visualize utility data, which is what I will continue to talk about. And I think this picture of this meme of Mr. Incredible really shows it very well. So first off, you have Mr. Incredible in all his fully 3D glory as an installed utility. And then as build summation happens, there is a degradation of the quality, and really a lack of information happens when you take the installed utility and put them into an utility map. You just flatten it all out, and then at the end, if you take the utility map and spray that onto the surface, there happens another loss of data. So I think this is what we have been looking into. Could we do this better? And just to give you an idea of what Rasmus was supposed to tell you about, was the 3D capture part of subsurface utilities. And this is where we question ourselves, could surveying of subsurface utilities be done easier and smarter by using 3D capture technology? And what the IT34 ended up doing was build this smartphone-based reality capture app that uses photogrammetry, and then make these really nice and detailed-looking 3D point clouds of as-built utilities. So really, when you compare that to this Mr. Incredible meme again, we could say that the 3D captured as-builts, they are actually now the installed utilities. They are like an exact 3D representation of him, whereas you can see that in the traditional way, what really happens is that this utility installation is we're living in a 3D world, right? But it happens to be compromised into this utility map. Okay, so what I wanted to to explore further in my PhD, especially about the visualization part, was that could I maybe make other or new kind of visualization methods that could display subsurface utility data in a more informative and understandable way. So to understand that, let me just introduce you some of the challenges there is with visualizing underground infrastructure. And one of them is that, as you can see here in the video, if you just naively display subsurface utility data as 3D models beneath the ground, even though these are correctly placed, it doesn't really seem right. It looks like these this displayed 3D models is somehow floating above the ground, and it has to do with what's called the parallax effect, that you try to visualize something behind an opaque surface, and this became even worse when you're also moving, where this parallax effects really become present. So of course, this is something that researchers and AR develops has looked at, and that's also why there's almost like a field of what's called X-ray visualization techniques, and one of them is, for instance, you can use a cutaway technique, just shown here in the picture, just like for instance the side vision is doing. Side vision is Trimble's side vision augmented reality product, where you make this surrounding box around the 3D model to then have it look like it gives this better depth perception understanding. Or you can maybe use some shadow projection where you actually place the utilities as seen on the pictures on the right, but you also make the projection to the ground, so you have an idea of where this utility pipe is actually situated on the ground. But when you look at it really, you can see that these visualization approaches was the same that has been done back in 2009. So there hasn't really been anything new, I would say. That's at least what I found one of the motivation to try to look in, could we maybe do another kind of AR visualizations? And also one of the big problem is that most AR systems today just use a planar ground surface estimation. So a lot of times these techniques, they don't really follow the actual terrain of the real scene, because they just estimate it as a planar surface. So the first part of this research was actually because I collaborated with IT34 and some utility companies in Denmark, because they have been using this 3D capture measure for documenting, surveying and documenting their subsurface utilities. So as you can see here, they have made a lot of these, they have captured a lot of these excavation holes. So now have a lot of these point cloud stores, and then use them, of course, to see. They use them as an as-built documentation, but they really also wanted to use them in the planning phase of new utility projects. So when they maybe come to revisit the same place, they have an idea of what is actually beneath the ground. So that was a perfect idea to try to take this into augmented reality. So here you can see we place the 3D point cloud on top of the street surface, and it's actually like kind of a time machine, right? So what we look at here is, from 6 months ago there was the excavation, but now we can visualize how it look like. And This is just another example of it, but it really provides an believable AI experience. And I would say that this is also due to the fact that, you know, we actually have something that was captured in this place, and then we perfectly align it again on the same place. So it kind of fits into the real world, right? And we also interviewed some of the professionals working with this, mostly excavators and yeah, just utility planners in the field. And they really liked it. Some of the pros was that it provided a clear picture of what is beneath the ground, and also something, yeah, and the possibility to see the utilities placements, the depth, and especially depth are very important, because most of the time from utility maps, depth is lagging. The width and material type, all these kind of things, they actually could just read from this realistic looking point cloud, and they just basically unlocks the dream of excavation before digging. The cons, of course, was that you of course need to capture the point cloud data beforehand, otherwise you can't display anything, right? So that's kind of a big limitation in terms of just using this everywhere. And it also, some also mentioned that it could actually maybe provide a false picture scenario. So for instance, if another excavator happens to have been excavating after the 3D capture documentation was happened, then of course, if what is shown in the AI use case now would be a false picture. And then also a big limitation in terms of adoption was that even though these point clouds are great, in Denmark at least, and I guess in a lot of countries and jurisdictions around the world, this is really not the legal data foundation. Mostly the legal data foundation is a system in place to exchange map-based utility data. So there's also maybe something about legal issues that they have to think about. Yeah. So, but yeah, and then the next step was really that we got this, yeah, really good feedback from this visualization method, and I thought, could we maybe make a good visualization method for common utility data? And I would say this is really one of my more philosophical moments. And one of them was, of course, that the common utility data is this 2D vector data. Just gonna take some sip of water. And yeah, but again, the problem is that, as you saw in most other the visualization methods that was demonstrated before in the background, previously, they usually relied on 3D data, right? But a lot of time you don't have the depth information attached, included in the utility data. So this was one of the limitations I work with. And really what came to mind was that could we maybe make an AI visualization method that was more relatable for the subsurface utility workers by resembling the visual appearance of real utility markings. And it was sort of playing on the same positive feedback from the other visualization method, where it looked exactly what they were used to see in the field, right? What they're used to look at, real excavation holes. So could we maybe make something in augmented reality that looked like real utility markings? Yeah, so for that we analyzed some criteria. One, the placement of the markings had to follow the ground surface. And for that, we relied on the newest iPads with the 3D LiDAR scanner on the rear to get this real-time 3D reconstruction of the ground. And through some fancy computer visual methods using raycasting and such, we could have the visualization follow this 3D mesh reconstruction that was generated directly from the terrain. And the other thing was that we want the markings to blend into the ground surface, just as the real utility markings. And for that, we looked into how software editor, photo editor software, just like Photoshop did, and we looked at some of the method called overlay blend mode effect, where you take one texture from the background with another overlaying texture and kind of blend them together. So we incorporated that into our shader development. And then we also wanted to follow the same utility marking language, so to speak. And by that, you looked into the standards of some industry guidelines, as seen here. I think this is actually some examples from the US. So follow the same styles and colors and symbols. And yeah, this is the result, which I think looks quite good. So input is GIS data, and output is this utility, virtual utility marking. And let's try to break it down. So you can see here that the LiDAR and the rear on the iPad generated real-time reconstruction, and by having that terrain into our pipeline, we could have it fit very nicely and closely to the real surface. And I think this is really clearly useful in these environments, in the constructed environments, because there's a lot of elevation change all the time, I can see here. And especially also, doing excavation. A lot of times, that in a construction project, the terrain really changes a lot. And also compared to traditional utility markings, one of the main limitation is that once you start to dig and remove the top layer, you also remove the real utility markings. And this is a more close-up look of how the texture blending looked like, and which is, actually came out surprisingly well. And we could maybe say that it's just a fancy gimmick, but I would say that it's some of the benefits is that it doesn't really obstruct the real environment. It really, blends in nicely with the real environment. I think that is maybe one of the key benefits of going with this approach. But there was also some limitations. For instance, here you can see on white surfaces with a rather light green color, the blending didn't wasn't that apparent. It wasn't that clear as it as we would have liked. And then also just some examples from the the design of the markings, styles and symbols and such. As you can see here, we incorporated that, for instance, if it was electrical cables, we had the right aberrations and stuff like that. So all in all, this was also something that was very comprehensible looking. The respondents said in the interviews, and they really felt that this was direct to their use when working in the field. And of course, also one of the clear benefits was that they really liked the stable visualization, that it was really closely aligned to the ground. So really no floating in the air effects. Cons, there was the lack of visualizing depth information, but kind of that was we didn't have the depth information, so it's kind of hard to visualize the depth information. But anyway, this was what some of the respondents response. So all of this work has mostly been done together with the Aalborg University, where I'm part of, and also from Graz University of Technology, where I work with some amazing researchers down there. And one thing that I haven't really talked much about, which I won't mention, won't go into depth with, is solving the problem of outdoor localization. And for that especially, the guys from Tychogras and AR4, we, in our prototype setup, we incorporated this sensor cube that could provide us with accurate outdoor positioning. So if you want to know more about this, I think you should reach out to Clemens Art here. He would definitely tell you more about how that how this device how this device help us achieve the good centimeter accuracy outdoor positioning. So yeah, conclusion was that in terms of the 3D capturing, it was, that part is, way better than conventional surveying in terms of that it's quite easy to do 3D capturing now, and there are so many, benefits from it compared to just using conventional surveying. And also in terms of one of the clear benefits was actually to maybe use these 3D point clouds or 3D captures models in general in augmented reality, and by shown here with the virtual daylighting approach. And what I would say that even though we always see 3D point clouds as something that doesn't have any structured data, it doesn't have any semantic and such and metadata attached. When really visualized in augmented reality in this use case and seen by the eyes of the professionals, they can generally retrieve a lot of information that at least I was surprised of, because simply because of the this is almost an exact 3D picture of how the utilities was installed. And for the virtual utility markings, I would say it's it's a step in the right direction, but it's maybe not the perfect visualization method. But it is at least, I think, a visualization method that is trying to be designed for the actual utility workers in the field, and play on the strengths on what they want to how they want to perceive and obtain utility information. So I think it's a step in the right direction. Yeah, and for future work, I would say that one of the things was that well, this is all good that we can now that I made this AR visualization method, but really the problem is a lot of times that the existing utility data we have is not accurate enough. But what is accurate is these 3D asphalt captures. So the idea is that maybe could we take these 3D point clouds and try to could we maybe understand them better and use them as a kind of validation source for the existing utility data, and maybe also just generally upgrading the existing utility data based on these scanned excavation holes. And I think one benefit, going back to augmented reality again, could also be to establish a more semantic link to accurate utility, traditional GIS utility data, which has a lot of valuable attributes, and then maybe display that in like a combined AR visualization prototype thing that, for instance, like shown here on this concept figure. Yeah, so thank you for this. And I can see now Rasmus is here, so I will just give the presentation now to Rasmus, and he will make presenter. Here you go.
And I unmute myself, so maybe.
Yes, I can hear you loud and clear, Rasmus.
So there, and So let's see which screen I'm sharing. Do you see my screen?
Yeah.
The one with the PowerPoint on?
Yes.
Yep. Perfect, Rasmus. Thank you.
All right. So now a little clock should be rotating. Time goes by. Yes, please apologize. Let me apologize. I was in the office, but I didn't feel well, so I had to drive home. So I hope it was okay that I take the last part of this. Stop me if I say something that you've already said, Lasse. Otherwise, I will just continue, and I will focus on the actual data capture and also the kind of functionalities and what we've done in order to set up a system where we can achieve a fairly quick data capture of consistent and usable geodata. So the first one here, the clock that runs and runs and runs, kind of illustrates one of the issues why we dived into this issue. Maybe Lasse touched on this, but in effect, we as private citizens, we see a lot of these digs all around the city all the time. And sometimes it's annoying, and sometimes you drive beside one of these excavations and you think, what is going on? Why didn't they just close that hole so I can go about my normal business? But the thing is that some work is going on, and sometimes we actually they are waiting on people to come and document the excavation, the results, the location of the pipes, and what it looks like. And the guy in the excavator, he often doesn't care about this, or it's not his job. So he waits for somebody else to come and do this documentation, and time goes by. So what we did was we looked at and see if there's a possibility of using something else to do this. And by now, we all run around with a mobile in our pockets. And the mobiles have, the newer ones have LiDAR scanners, and also newer ones have excellent cameras. So using a simple thing as a camera and doing photogrammetry, as we've done through aerial photography and mapping for many, many, many years, using kind of the same algorithms, just using for terrestrial laser scanning, terrestrial photogrammetry, we can calculate a point cloud from the mobile phone. So what we set about to do was to invent or set up a mobile app, which doesn't really do anything but capture a video, a location and a video. And from that location and video, we simply just can calculate a point cloud from this. It's actually pretty accurate, and I'll show you some examples here later on. But from a normal utility excavation, recording a video where you walk just around this excavation and record it from all sides takes about somewhere between 30 and 45 seconds. All cameras or all mobile phones is equipped with a GPS, so we can kind of log the first initial location of the video and also have some initial values for the photogrammetry calculations. So that means that from the very beginning, we have a location of the point cloud, and we also have kind of a fairly good rough first point cloud, which is calculated. That can be, the result can be made better, and it can be made better through normal ground control points, or something which we've implemented also, which is a scale bar and a tie point. So this is the top view of a point cloud, which has been calculated from a 35-second video. You can see the numbering here, 70, 71, 72, and 73, and a small dot next to it, which is the GCP, the ground control point, which has been measured with a normal, regular professional GPS setup. So we have the coordinates, which enable us to georeference the point cloud. And then we have the scale bar, which directly give us a relative accuracy, which is very, very good. And in in the bottom of the trench, we have started implementing this tie point. Just a second, I'm just going to clear my throat. So we implement the tie point in the bottom of the trench, often because the trench itself, or in the bottom of the trench, we have a lot of mud, we have a lot of water, we have a lot of kind of similar environment. By introducing this tie point, we get a very good and clear target, which we can use for tie points, which clear up the point cloud very much. So it's a very the noise is reduced quite significantly. And let me see here, the next one. So actually, in effect, this smart survey is a complete documentation through a 30, 35, 40 seconds video, because we calculate the point cloud, but the video itself is just a lot of images set up. So it's often 30 frames per second, which means that we actually have 30 images for every second that we've recorded. Taking some of these images, not all of them, it's quite sufficient just to take maybe, I don't know, 4, 5, 6 from every frame. We can do this calculation, but that also means that we have still images from all of these locations, which we can use for inspection at a later stage. One of the issues that it solves is that in many situations, when the surveyor or the contractor digs the hole and installs the pipelines, he also takes a few images, but not so many, maybe 10, 15, whatever. But often they end up on the iCloud or the gallery of the phone, which is it has been taken with, and it doesn't really make it back to the document handling system or anything like that. So it can be kind of lost. So the thing itself, we record a video, we make sure that it's georeferenced through control points, we implement the scale bars to make it relatively very accurate, and we secure it for documentation. So what do we actually do? Because what it solves is that the contractor, he does not need to wait for the survey. He can just cover up the hole and continue with his work. So what we actually provide is kind of a look beneath the surface. As you all know, as soon as the work is done and the hole is filled up, then the pavement is put over it and we can see what's beneath. Lasse has made a very, very good way of either looking beneath the ground or kind of projecting the underground onto the surface of the ground and doing this kind of making the data visible again. Yeah. So what I wanted to show now was that, as I said before, the yellow markings here actually indicate where the video recording has been done. So for every one of these yellow markings is an image with showing the inside of this trench. And you can see the scale bar in the background. Just to illustrate that it is actually accurate, it's 50 centimeters between the 2 points. And when we do a measurement, it is 50 centimeters between these 2 points. And that means that every measurement inside the point cloud is actually very accurate distance-wise. When we put the point cloud and the image between beside each other, you can see that from a distance it looks quite similar. But when we kind of want to see and zoom into the details, the point cloud itself becomes more scattered. And that's just the nature of the point cloud. It's a very good tool to do the distance measurements or area measurements or take coordinates. But the image itself contains a lot more information. So by putting these two next to each other, we get a very good data set for doing the measurements, and we have a very good data set for doing the inspection. The measurements can be done in the point cloud, so we can have clear and accurate measurements between points of interest. It could be the pipeline itself and the height difference between the two water pipes. And we can also start to take coordinates. This means again that whatever was not measured while the trench or the dig was open, as soon as we have, or as long as we have this 30 seconds video and the control points, then afterwards we can do all the measurements and all the documentations and all the data feature capture that we want. The trench does not need to be open. And why is this important? It is actually important because in reality, we know a lot about where our pipes are. And Lasse, you probably touched this also, but let me just quickly run through some of it. This is an extract from the Danish pipeline database. And the green one and the blue ones are the ones which are known, but there's actually a lot of data which is missing from this database. And when you dig a trench, you will meet these pipes nonetheless, even though you don't know that they exist. There's also a lot of other issues or stuff about this data set that we don't know anything about these things. But as soon as we have a point cloud and we do have this data, then we can start and elaborate and do more registration. And in effect, if anybody wants to revisit this dig, this trench, instead of just extracting the line features from the national database, they could also go and look at the point cloud and see that there are actually something else that they also need to be aware of, so they don't dig and rip these pipes along. As I said, we can do all the feature capture that we want afterwards, coordinates, heights, distance, areas, whatever. And of course, like anything else, the data is integratable in the GIS platform. So whenever you have a QGIS, the data can be streamed through VFS as a line string for the pipelines, or we can also just implement and use a simple orthophoto calculated during the point cloud calculation, which is also just streamed in as a VMS layer in the GIS. So now you get a visible setup where you can see, together with your current registration, also new pipelines or pipelines you did not know exist. Of course, I represent the IT34, LE34 company, and we've also made our own 3D web viewer for this, where we can take the lines into 3D, we can integrate them with the point cloud, and we can see how things work, how things look in reality. And to finish it all off, it's actually quite easy. It's called Smart Survey because it is smart and it's a survey. And all you do is actually just install the app, and then therefrom you're good to go. Of course, adding the type points, adding the GPS control points, you just increase the reliability of your data. But from the very, very first recording, you have a very good documentation of the initial dig itself. So that was the very, very quick introduction of what I had to say about the way that we have set up a production and a data capture for documenting trench digs and making it available on a fairly large scale.
Fantastic. Thank you, Rasmus. This is Mark. again, I'd ask if anybody in the attending have got any questions, please just type it into the questions box. But a quick one from myself. You know, it's been fantastic to see that the work you've done. Has there been any work or talk or measurement on the kind of savings that the utility companies have seen or potentially would see using this kind of technology or using this solution? Has there been any kind of thoughts on ROI?
Yes, it has. We license this for a yearly fee, and it's not very much. But what our clients can see is that the time that they need to have the trenches open and wait for the surveyor to come and do his measurements before they can close the dig, maybe it takes an hour, maybe it takes 2 hours on the day, or if it's the next day, they need to set up what would be the English explanation, when you set up the barriers so people don't fall into your dig, and you put up all kind of restrictions and safety measures for this. If it's possible to set up like this system where the excavator, the guy who's driving the excavator, he actually just digs the hole, and just before he wants to fill it up, he puts 4 markings on the ground. He records a video and uploads the video, and then he actually fills the hole right after that, because the GCPs, as long as they're visible, they can be measured the day after. It's not necessarily on the same day, but he can close the trench right after he has captured the video. And that means, at a conservative estimate, it on the day, if they're waiting for an excavator, for a surveyor, you save about maybe 2-3 hours work of an excavator just being idle on site. If it's the next day, you can, by using this one, you can remove your barriers right away, which is also kind of saving you a couple of hours work. So it's difficult to put a precise amount on this because it varies from country to country, from contractor to contractor. But you can easily estimate from your own local environment what a couple of hours work of an excavator being idle is like. Does this kind of answer your question, Mark?
Absolutely, yeah. No, thank you, it does. I guess there's also slightly more difficult intangible savings, but having the latest information kind of kept up to date rather than those drawings that we know go out of date really quickly has longer term implications and savings as well. So definitely kind of the time, I think definitely the number of mistakes, and definitely having a good digital footprint for the future are all benefits that will stack up over a period of time. Sorry, Leslie, did you want to add to that at all?
No, yeah, I think that was what Rasmus told was the clearest and most profound example of the savings when using the 3D capture. And just, I didn't do any return of investment studies regarding the augmented reality, the visualization of either these 3D point clouds or just traditional utility data. But I asked the excavators also, do you think this would prevent excavation damage? And clearly, if you are at a visiting, if you are going to revisit a dig site where you have this 3D capture available and can visualize it, there was like, for sure this would be so helpful. And also just something that you maybe not think of is that you can actually also see in which way is it better to dig down to the utility pipe on the left side or the right side, because you can actually see where is the empty space. And this is all of these things they told me when they looked at this that they could use and implement in how they are working when they're working in the field. So yeah, I can really put a number on it, but they were clearly excited about having this technology available for them. So yeah.
Fantastic. Yeah, thank you.
I'm
There's
probably
another question. Oh,
sharing
sorry,
my screen here. I'm probably still sharing my screen, right?
Yep.
Yes.
So you see now the live point cloud. This is actually from a recording I did this morning for a contractor. He's doing a pipe dig inside the trench here. So just to bring in a kind of a practical one, I've put a marking here on each side of this one, and then the scale bar here in the middle, right here. And this is done just from capturing the video from an iPhone 13 Pro, walking one trip around the excavation. And if I dig down here, we've included a tie point here down very deep in the trench to make sure that the noise is not that much. We still have some noise in the point cloud, but this is the actual point cloud just calculated from this one. It's deep inside the ground. It's about 5 meters down below, like this. So it's just to show you that it's not just these small 1.5 meter deep digs that it can actually solve the issues. Sorry.
Yeah. Excellent.
You had a question.
There's a couple of other questions coming in, so let me ask you those as well. I'm just way at the time as well. Do the markings work when there's obstacles in the way, like cars on the road?
I guess is that for the augmented reality markings? I guess so.
I'm guessing so.
Probably. Yeah. Yeah. Well, if there is a car like static, stationary, they will just the markings will just go over the follow the curvature of the car. It's yeah. The input is the real-time 3D reconstruction from using the lidar from the rear lidar from the iPad and the newest iPads and the newest iPhones. So whatever that what it picks up, it would be visualized on top of that surface.
Okay, that makes sense. Another quick question. How long has this been used in the field, and how many scans have been collected?
It's probably we've been using this and developed it during the past 3.5 years. And we have, together with a couple of companies in Denmark and Sweden, I think we have just around maybe 4,000 different individual excavations, utility excavations like this. Some are very narrow, just for water utility maintenance, and some are trenches ranging up to 75 meters long in each section.
Okay, perfect. And just a comment here. This is a nice implementation, what I describe as civil engineering, which I agree with. It also aligns with the tools and use cases that have been used in the medical industry, specifically as it relates to mapping and navigating human vascular structures. So that's from one of the area members at Medtronic as well. So I think what you've done is very interesting, but like I've said at the start of the presentation, AR is actually across all sorts of different industries as well. So this could be reused potentially for other bits. I think one last question, because we're getting close to the top of the hour. Have you tried using this method of visualizations along with the aggregation of GPR, ground penetrating radar data, to further improve the quality of the results?
No. Yeah, so taking data captured from GPR scans, I guess, and then
supplement it, or so,
then you do. I haven't done it, and I guess probably also because I think mostly in Denmark, my experience when talking with excavators was that they just didn't want to use GDPRs. They like the idea of it, but in reality, when they tested it, it was just too resourceful. Maybe not in terms of the equipment is expensive in itself, but really also the time, reading the radiographs, the graphs, and then transforming it into something meaningful, utility data. That is at least what they responded in Denmark. And so also because of soil conditions in Denmark is quite tricky, so it isn't always the best solution. But I'm not. I haven't. I limited myself for really going into that topic or that data source.
That's great. Okay, I think we're close to the top of the hour, and I'm sure we've got other calls, but I just want to thank you both, Lasse and Rasmus, for a really interesting presentation. The recording will be made available on the area website and the area YouTube channel after this, and we'll send an email to everybody who's registered and participated. So congratulations on some great work. I look forward to continuing following and the area, showing what you've been able to do. And thank you very much, and thank everybody for listening. I hope you find that very useful, and I'm sure I'll speak to a lot of you again soon. Okay, thanks everybody.
Thank you very much. It was a pleasure.
Thank you. That's great. Thank you.
Sure, a pleasure.